You should read this material again about the need for complex numbers, and just remember that we defined the complex number I. It's called the imaginary unit. The imaginary unit is I, and I is the number whose square is -1. So I squared equals -1. So in order to become good at working with complex numbers, make sure you can identify the real part and the imaginary part of every complex number. A complex number is a number of the form a plus bi, where the number a is the real part and the number b is the imaginary part. So in this first example, the real part of this number is 2, and the imaginary part is 6. In the second example, the real part is 3, and the imaginary part is -1. In the third example, the real part is 0, because this is a pure imaginary number. The imaginary part is -2. So this one is pure imaginary, because the real part is 0. We call it a pure imaginary number. And this example, the real part is 5, the imaginary part is -7. And in the final example, the real part is 3, and the imaginary part is 0. So this is a real number. It's a real number. So if the imaginary part of a complex number, these are all complex numbers, if the imaginary part of a complex number is 0, then the complex number is a real number. And if the real part of a complex number is 0, then that complex number is called a pure imaginary number. Now you need to be able to do arithmetic with complex numbers, and that means you should be able to add, subtract, multiply, and divide. Adding and subtracting and multiplying are quite simple and very intuitive. To add two complex numbers, you add the real parts together. So here we have the real part 2, and we'll add that to the real part 3. So we'll have 2 plus 3 for our new real part. The imaginary parts are -5 and +4, so we're going to add the imaginary parts, -5 plus 4, and we add the coefficient I there to indicate that this is the imaginary part, and so we end up with the number 5 minus I when we simplify this. Okay, so for the next example, we're going to add the real parts, which are 7, and now we have to be careful because there's a minus sign there. So 7 minus 5 is 2. That'll be the new real part. The imaginary part is obtained by adding the imaginary parts. But again, be careful. This is -1/2 minus 3/2. So let's just write that down. We have -1/2 I minus 3/2 I. So when we add those two imaginary parts, we have the real part 2, the imaginary parts just add up to -4/2, which is -2I. So there's your complex number. So you have to be very careful with those differences. Now the product of two complex numbers is, again, very intuitive. It's just like FOILing for a binomial. So you just multiply 7 times 4 plus 2I, 7 times 4 plus 2I, and then you multiply minus I times 4 plus 2I. So when you multiply 7 times 4 plus 2I, you get 28 plus 14I. And here you get minus 4I, and then minus 2I squared. Well, remember that I squared is -1, so this last term is actually +2, and that's a real number, so we can add that +2 to this 28, and that'll give us 30 for the real part, and the imaginary part, we're going to add the two imaginary parts of this number, which are 14I minus 4I, and that gives us plus 10I. So 30 plus 10I is the complex number that's the product of these two complex numbers. So you can also look at powers of I. So it's a little cluttered right now, but you can see I have, suppose you have I cubed, and you want to write that in the form of a plus bi. Well, I cubed is I cubed is I times I times I. But I squared is negative 1. So this is negative 1 times I, which we can write as negative I. So that's how you would find powers of I. There are some homework problems where you have to do that. So I thought I'd just show you this one example and see if you can figure out some of those homework problems. Okay, so the next term that we need is the term complex conjugates, and the reason we need that is because we have to know what these are in order to do division of complex numbers. So we've got addition, subtraction, and multiplication. So in order to do division, we need to have one more term to understanding, and that term is the phrase complex conjugates. So what are complex conjugates? These two complex numbers are called complex conjugates. Notice that the complex conjugate is simply simply has the same real part. Notice that the real parts of these two numbers are the same. They both have real part A, but they have opposite imaginary parts. So where one of them has imaginary part B, the other one has, the conjugate has imaginary part minus B. So the complex conjugate of a number just simply means keep the same real part and use the opposite imaginary part. Notice that a plus bi times its conjugate a minus bi equals a squared plus b squared, and I ask you to verify this on your own. Make sure you do that. Show that when you multiply a plus bi times a minus bi, you get a squared plus b squared. The important thing about this is that this number, a squared plus b squared, is a real number, because remember, a is a real number and b is a real number. So the nice thing about complex conjugates is that if you multiply a complex number times its conjugate, you always get a real number. This is just a note on notation, so check that out. But we use complex numbers to evaluate division problems. We use complex conjugates to evaluate division problems in the complex numbers. So we have to express our result here. This is a division problem. We want to express the result in the form of a complex number, a plus bi, which means we cannot have any denominators that have complex numbers in them. So we look at this expression, and it's not in the form of a plus bi. We have this denominator down here that's a complex number. We would like the denominator to be a real number. Well, we have a way of getting a real number from a complex number. That's multiply it by its conjugate. So we're going to take this expression and multiply it by 1. Again, we're using the mathematician's trick of 1. And now we're going to use that trick with complex numbers to adjust this fraction, if you will, so that it has the proper form, a plus bi. And again, to do that, we need to multiply by 1, and we're going to write 1 this way. We're going to use the conjugate of the denominator, and we're going to multiply both the numerator and denominator of our expression times that, because that's what is the mathematician's trick of 1. It gives us what we want. So when we do that, let's just show some steps here. We have 1 minus 2i times 1 plus 2i. Well, if we just FOIL this out, we have 1 times 1 plus 2i, which is 1 plus 2i. And we have minus 2i times 1 plus 2i. So that's going to give us minus 2i, and then minus 4i squared. I guess I didn't really need these parentheses. They're kind of just cluttering up my denominator, so I'm just going to get rid of them. Don't want them. Okay, so now I can see that what I have in the denominator is actually a real number, because this plus 2i and this minus 2i add up to 0. I squared is negative 1, so this back number is actually 4. And so the denominator is actually 1 plus 4, which is 5. So what's the numerator? Well, the numerator, I have to multiply these two complex numbers together. So if I do that, I get, let's see, 2 times 1 is 2, 2 times 2i is 4i, negative 3i times 1 is negative 3i, negative 3i times 2i is negative 6i squared. And once again, I have I squared, which is negative 1, times negative 6. So this number here is actually 6, and that's a real number. I add it to that real number 2, and I get the real part, 8. The imaginary part is 4i minus 3i, which is I, so I get 8 plus I. And now to write this in the form of a plus bi, I have to separate this into two separate fractions. So I get 8 over 5 plus 1/5 I. So A is 8 over 5, and B is 1 over 5. So I've identified the real and imaginary parts of this complex number, which was obtained by a division problem. Second example, we have 4 plus 6i divided by 3i. We multiply again using the mathematician's trick of 1, and this time we'll use the conjugate of 3i, which is negative 3i, and so we're going to multiply both numerator and denominator by negative 3i, and that's going to give us, by the distributive property in the numerator, negative 3i times 4 plus 6i is going to be negative 12i minus 18i squared. And in the denominator, we have positive times negative 3, so that's going to be negative 9i squared. So again, in the numerator, we have this 18i squared, which is actually 18 times negative 1. Combining with that negative sign gives us positive 18, and that's a real number, so that's the real part, 18 minus 12i. The denominator is also real, negative 9 times I squared is negative 1, so negative 9 times negative 1 is positive 9. We break this up into two separate fractions, 18 over 9 minus 12 over 9i, and now just reduce your fractions. 18 over 9 is 2, and 12 over 9 is 4/3, so 2 minus 4/3 I is the simplified expression for this division problem. Working with square roots of negative numbers is sometimes kind of tricky, so you have to be careful when you have a negative number inside of a radical expression. The first thing you want to do is realize that this is equal to the square root of negative 1 times 25. That negative 1 inside of the square root becomes I outside of the square root, so you have I times the square root of 25, and we know the square root of 25 is 5, therefore this number is 5i. So again, we're going to be very careful when we evaluate negative square roots. First, we're going to remove the negative 1 inside the square root. It becomes I outside of the square root. So this first factor is I times the square root of 3. The second one, again, there's a negative sign inside the square root. That becomes an I outside the square root, and so now we have 12. So square root of 12. We can simplify the square root of we can simplify this now by multiplying this I times this I. That gives us I squared. And then we have the square root of 3 times the square root of 12. That's the square root of 36, which of course is 6. I squared is negative 1. The square root of 36 is 6, and so that gives us negative 6. So final example here, we're going to remember to remove the i's first from the negative square roots here. So we're going to get 3 minus I times the square root of 5 for our first factor, and 1 plus the square root of negative 1 is I for our second factor. And I will leave this for you to complete on your own. You just have to multiply these two complex numbers and see what you get. So it's, again, very similar to foiling for binomials. So just do that. Okay, now for finding solutions of quadratic equations in the complex numbers, we can solve equations by many methods. Here's a simple one, x squared plus 49 equals 0. One way to solve that equation is to isolate the variable term. Since there is only one term that has the variable, we'll just isolate that term, so we end up with x squared equals negative 49. Now that we know about complex numbers, we can go ahead and find the value of x that's equal to plus or minus the square root of negative 49. Well, the square root of positive 49 is 7, so the square root of negative 49 is 7i. So we end up with x equals plus or minus 7i. So those are the two solutions of x squared plus 49 equals 0. Remember, once you know the solutions, you can write the factored form of x squared plus 49. And if you're thinking of x squared plus 49 as a polynomial, once you know that you have solutions or zeros, you can write x plus 7i times x minus 7i, and that should equal x squared plus 49. You want to verify that and make sure that you understand that that's the case. Our next example is x squared minus 4x plus 5 equals 0. This one we'll do by completing the square. So we have x squared minus 4x equals negative 5. So to complete the square here, we need to add 4 to both sides. We add 4. Now we have a perfect square. X minus 2 squared equals negative 1. Now take the square to both sides. X minus 2 equals plus or minus square root of negative 1. And move the 2 over. X equals 2 plus or minus the square root of negative 1 is I. And those are your two solutions. Completing the square is really easy. You should be happy to complete the square. Oh, I thought I was erasing that. There we go. Okay, the last one, 2x squared minus 2x plus 1. This one I will use the quadratic formula. A is equal to 2, B is equal to negative 2, and C is equal to 1. And so x is equal to the opposite of b, 2, plus or minus b squared, 4, minus 4ac, a is 2 and c is 1, over 2a, which is going to be 4. So we'll simplify that. 2 plus or minus. 4 times 2 is 8. 4 minus 8 is negative 4. Square root of negative 4 divided by 4. Well, the square root of negative 4 is 2i. So we have 2 plus 2i over 4. We separate that into two separate fractions. 2 over 4 plus or minus 2 over 4i. And simplify the fractions. 2/4 is 1/2. So we get 1/2 plus or minus 1/2 I. The last part of this is the roots of unity, and we did the square roots of 1 and showed that x squared equals 1 has two solutions, positive 1 and negative 1. We also looked at the fourth roots of 1 as the solutions of the equation x to the fourth power equals 1. So in finding the fourth roots of 1, we solve the equation x to the fourth power minus 1 equals 0. If you just add 1 and get x to the fourth power equals 1, you might only find two solutions. So instead, we'll factor this as the difference of two squares. X squared minus 1 times x squared plus 1 equals 0. X squared minus 1 can be further factored into x plus 1 times x minus 1 because it's the difference of two squares. But x squared plus 1 can't be factored in the real numbers. However, we know that if we have the equation x squared plus 1 equals 0, to find its zeros in the complex numbers, we can subtract 1. X squared equals negative 1. And so now x equals plus or minus the square root of negative 1, which is I. So actually, we can factor x squared plus 1 as the sum of two squares in the complex numbers as x minus I times x plus I. So now we see we have four factors, and each of those factors gives us a 0. This gives us the 0, negative 1. This factor gives us the 0, 1, which we already knew were fourth roots of 1 because negative 1 to the fourth power equals 1 and 1 to the fourth power equals 1. But now in the complex numbers we see that we have two more roots of 1, fourth roots of 1, and those are I and negative I because I to the fourth power is also 1 and negative I to the fourth power is also 1. So we have four fourth roots of 1 and we have found them. So our next adventure is to find the cube roots of 1. So let's find the cube roots of 1. Let me erase all this. Finding the cube roots of 1 is equivalent to solving the equation x cubed minus 1 equals 0. X cubed minus 1 is the difference of cubes, and we factor that as x minus 1 times x squared plus x plus 1. Now this factor, x minus 1, gives us x equals 1 as a solution. That's the real number solution that we already know. 1 cubed equals 1. This factor will give us the complex number solutions, and we'll use the quadratic equation to solve that factor equal to 0. So if we solve x squared plus x plus 1 equals 0, using the quadratic formula, a is equal to 1, b is equal to 1, c is equal to 1. And so therefore we have x equals the opposite of b, negative 1, plus or minus b squared, which is positive 1, minus 4 times a times c, a and c are both 1, over 2a. And when we simplify this, we see that this part is imaginary. That's 1 minus 4, which is negative 3, and the square root of negative 3 is I times the square root of 3. And so we end up with x equals negative 1 plus or minus I times the square root of 3 over 2. And we write this as two separate complex numbers, and those we separate that into the two fraction parts. We separate the fraction x equals negative 1/2 plus or minus the square root of 3 over 2i. These are the other two cube roots of 1. Notice that these two numbers are complex numbers, and they are complex conjugates as well. So there are 3 cube roots of 1. The one that's the real number that we all knew. Until yesterday, we did not know that there were also 2 complex numbers, such that when you cube them, you get 1. As an exercise, you should consider each of these numbers, negative 1/2 plus the square root of 3/2 I, and negative 1/2 minus the square root of 3/2 I. As your own exercise, you should take each of those two numbers individually and raise them to the third power, and show that when you cube either of these two numbers, you will get 1. And that's what we mean by those numbers being cube roots of 1. When you cube them, you get 1. As your extra credit assignment, should you choose to do it, you will be answering this third question, or this third hypothesis. How would you find the 6th roots of 1? I want you to actually find them. How many are there? I want you to actually find them so you know how many there are. And then, as the piece of as the big piece of this question, make a conjecture about the number of nth roots of 1. So no matter what the number n is, whether it's you wanting to find the cube roots or the 4th roots or the 5th roots or the 6th roots, whatever root number you want to find, you should be able to come up with a conjecture about how you think that's going to work. Make a conjecture about the number of nth roots of the number 1.